Okay, suppose we have random variable y and random vector x, which is k by 1 vector, and another random variable we call epsilon. Actually, it's L times, and epsilon is normally distributed. And we know that y is equal to x prime beta 0 plus epsilon. So that's the data generation process, where beta 0 is k by 1 vector of the true value of the parameters. And from this data generation process, we have a sample yi xi prime, which has n observations. So now our task is to estimate beta 0, the true value of the parameters from the data we have. To do so, let's first set up the empirical model. So yi is equal to xi prime beta plus epsilon I. I is 1 until n, so we have n observations. Or we can write this in a more compact matrix form, so which is y is equal to x beta plus epsilon. So we can essentially, what we are doing is let's stack all this together. First observation, second observation, so on and so forth until n. So this is called y, which is n by 1 vectors. This is called x, which is n by k matrix. This is called epsilon, which is n by 1 vectors. So we know that y is y1 until yn, x is x1 prime until xn prime, so n by k, or it's actually equal to x11 is 1k, x21 to x2k, xn1 to xnk, and epsilon is epsilon 1 until epsilon k. Okay, so now we have this. What we have is we have a data like this, and we form an empirical model. Y is x beta plus epsilon, and our task is to estimate the beta 0. How can we estimate the beta 0? Let's first visualize the data. Suppose the data we have yi xi. We have data look like this. By looking at data, I hope you agree that we can, let's say, okay, we want to estimate beta. So what about, let's do it this way. Let's draw a line. Draw a line or choose beta. Saying draw a line is the same as saying that choose the beta. to fit the data points as well as possible. Okay, now you need to ask, what do I mean by as well as possible? I need to be precise. Okay, to see as well, let's look at the data, look at the graph. Say, look at the first data points. This point corresponds to, let's call it x1, and the associated y1. Okay, according to the red line I just draw, so the corresponding y, the y that corresponds to x1 would be this. Let's call it x1 hat, and we can easily see that there's error here, and this error is positive. Okay, let's look at another point. Say this point, let's call this x2. Associate x, associate y is y2. At x2, according to the red line, the associate y should be this y2 hat. And we see that now there's error as well, and the error is positive. Okay, let's look at this point, x3. Let me erase something, because otherwise it's going to be too messy. Okay, x3, the associate y, let's call it y3. According to the red line I draw, x will be y3 hat, and we see that now there's again the errors. The error is negative. So no matter how well we draw our lines, there are always errors. Some positive, some negative. So what about, let's draw a line, let's choose beta such that we make the sum of all these errors as small as possible, or choose beta to minimize the sum of errors. No, this is actually not a good idea, because now if we sum all this error up, positive one will cancel out with the negative one, which is not a good idea. So let's say, draw a line, before summing them, let's square the errors and sum them up, and then choose beta to minimize these square errors. So what we want to do is choose beta to minimize sum of square errors. And this is actually why this is called ordinary least square estimator. So let's derive the estimators. So we know that we have this empirical model. Or in metric form. So epsilon's error, so errors, square them, sum them up. So we want to actually minimize this quantity by choosing beta. Okay, so this is in metric form. This is just epsilon prime times epsilon. So we know that epsilon prime times epsilon is equal to epsilon 1, epsilon 2, epsilon n times epsilon 1, and so this sum is just this is just the sum of squared errors, and plug this one in here. So it's y minus x beta prime, y minus x beta. So we want to minimize this quantity, the sum of squared errors. This is y prime minus beta prime x prime. Y minus x beta. The first order condition, differentiate the quantity with respect to beta. Dq over d beta. So know that dq over d beta is k by 1 matrix. Okay, so we want to differentiate q with respect to beta. Okay, let me just take this one, multiply this inside. Y prime y minus y prime x beta y minus beta prime x beta. So let's look at this equation. So there's a beta here, there's a beta here, there's a beta here and here. So the first term does not depend on beta, it dropped. So these terms is a linear function of beta. So we get negative x prime y. So k by n by 1. So it's k by 1. Then the third term, similarly, is a linear function of beta. So it's negative x prime y. The fourth term is the quadratic function of beta. So it's this is positive, negative minus beta prime x prime times negative x prime beta. So this is positive. Okay. So it's 2 times x prime x beta. Okay. Or is equal to minus 2x prime y. Okay, set the first order condition, set the first derivative to 0. And you should know that this is a quadratic form, so the second order conditions are satisfied. I won't check it, but I'll leave you to check it. First order condition implies that x prime x beta is equal to x prime y. So now we want to invert this x prime x, and here's one of the assumptions that we needed for the OLS estimator to work. So x prime x, which is k by k, is full rank. Is of full rank. Which means the determinant of x prime x is not 0. Or in other words, the xi1, xik, they are not multi-collinear with each other. So no multi-collinearity issue here. Okay, let's invert it. So beta is x prime x inverse x prime y, and I'm going to put a hat on top of it to denote that it's an estimate, and this is what we call it ordinary least square estimator. And you should know that it depends on data, so it's a random variable. In contrast, the true value beta 0 is not random variable; it's a constant. Okay. So now we have this estimator, and this is feasible because we observe x, observe y. So the estimator, we can calculate a beta from the data. Right, okay, so now the next step that we want to show is that this beta hat, this estimator works. Okay, to do so, let's look at the means. Okay, let's take an expectation of beta. Remember, beta hat is random vectors. Okay, and we know that y is equal to x beta 0, the true values, plus epsilon. Okay. Multiply inside. And this cancels out of this. So it's beta 0 plus. Okay, let's bin of beta hat. Okay, let's use law of iterative expectation to write this expectation as the outer expectation taken with respect to x, the inner one that's conditional on x. For the inner expectation, because we are conditioning on x, so we treat x as constant, so let's move it out. Okay, so here's the second condition we need for the OLS estimator to work. And this is actually, we need this to be conditional on x, the epsilon, the error terms to have mean zeros. Or this actually implies that epsilon and x are uncorrelated. This is an important assumption we need to have. Or x is exogenous. If this assumption, this is actually an identification assumption. If this assumption fails, then we call x. If not, then we call x is endogenous. And we need to use other technique, other methods to estimate the parameter of interest. Okay, let's assume this holds. So previously we recall that previously we have a condition where x prime x is of full rank, which means there's no multi-collinearity issues. Now the second condition we need, or second assumption we need, which is an identification assumption, which says that E epsilon condition x is 0, or epsilon and x are uncorrelated. Alright, given this assumption, we know that the expectation of beta hat is equal to beta 0, the true value. So this is 0. So all the remaining terms disappear. Alright, so recall what we are doing now is we want to check our estimator, OLS estimator, whether it works. In the first one, we find that under those two conditions, beta hat, the expectation of beta hat is beta 0. So we call this estimator unbiased. Okay. The second thing we want to check is that we want if our sample size increase to infinity. Essentially, in the end, we want our beta hat, our estimator, to be closed to the true value in certain sense, or in a probability sense. Okay, so we want as in approach infinity, we want this beta hat converge in probability to the true value. Again, recall that beta hat is a random vector. It's random variables, a vector of random variables. Beta 0 is constant. Okay. Convergent probability. What do I mean by convergent probability? Essentially, I'm meaning that the event that beta hat, the difference. Okay. Basically, I mean that okay, the distance of beta hat from the true value. This is Euclidean norms, Euclidean distance. Okay, the event of this is bigger than, say, epsilon. Okay, I can choose fix epsilon positive, any small numbers. So this event, the probability of this event happened will be 0 as n approach infinity. That's what I mean. Okay. Alright, so let's check whether as n increase to infinity, beta hat will converge in probability to beta 0. And actually, if that's the case, we call that beta hat is consistent, a consistent estimator of beta 0. Okay, let's check this. So we know beta hat is beta 0 plus x prime x inverse x prime epsilon. Okay, what I'm going to do is I'm going to divide inside the bracket. Let me divide it by n. Then modify n. Okay, so now we have two terms here. This term, let's call this term 1. This term, second term. The reason that I want to divide it by n is because I want to apply a very powerful tool, which is called law of large number. Okay, what does law of large number says? Basically, it says that if we have a sequence of independent, identical, distributed RID random variables, which has a mean mu, with mean mu, then sum of them divided by n, average, converge in probability to its mean mu. Okay. Okay, let's check the first terms, 1 over n x prime x. Note that x is x1 prime, x2 prime, xn prime, so it's n by k. So x prime x is x1, x2, xn times x1 prime, xn prime. So this is just sum of xi prime. Okay, so 1 over n x prime x is just 1 over n. So we see that we can write this. We see that this is actually an average of independent RID random variable xi prime. Okay, and the law of large number says that this converge in probability to its means. Let's call it this mu x. Okay, mu x. This is k by 1. Sorry, k by k matrix. That's the first term. Second terms. Again, we can see that this is an average of our RID random variables. And by this assumption, this identification assumption, we know that for each I, this is equal to 0. So low or large number says that this will converge in probability to its mean, which is 0. Okay. So now we have, by using the low or large number, we observe that these terms converge to mu x. These terms converge in probability to 0. So these terms converge in probability to 0, the whole terms. So we see that beta hat converge in probability to beta 0. As in approach infinity. So indeed, beta hat is a consistent estimator of beta 0. Alright, the next thing we want to look at is to check in the limit what happened to what's known that the beta hat is a vector of random variables. So we want to check that, and we know that beta hat converge in probability to beta 0, which is not a random variable, which is constant. So in the limit, the distribution of beta hat will be degenerate. Okay, but what about let's scale beta hat a little bit differently to see what happened in the limit? What happened to the distribution of beta hat? Okay, so what I want to do now is, let's say beta hat minus beta 0. Remember, beta 0 is the mean of beta hat, and this scale it by root n. Okay. Inverse x prime. So this, okay, no. X prime x inverse x prime epsilon. Okay, let me, for x prime, divide x prime x by n. Over root n. So this is root n beta hat minus beta 0. And as n approach infinity, we see that this converging probability to mu x. And these terms, so recognize x prime epsilon is actually a sum of RID random variable. So x prime epsilon is a sum of random variables. And so now we need another powerful tool, which is called central limit theorem. Again, it says that this is y1 yn, which is RID random variable with say mean 0 and the finite second moment. And then sum them up. Scale it by root n, not by n. If it is by n, then okay, sum them up. Scaled by root n, not by n. If it is by n, then we know that the low large number will say that it converge in probability to its means. So if scaled by 1 over root n, then we the central limit theorem says that it converge to a normal random variables, normal distributions. Okay. Okay, so we apply the central limit theorem to 1 over root n x prime epsilon. So we know that it converge M distribution to a normal random variable. The distribution of normal random variables. Let's call this sigma squared. Hence, as n approach infinities, the whole terms converge to a normal distribution. Okay. So this is a limit distribution of root n beta hat. Okay. The last thing we want to do is we know that beta hat is random variables, so we want to derive its variance and covariance matrix, and the mean of beta hat is equal to beta 0. Okay, so let's calculate the variance covariance vector matrix of beta hat prime. So this is k by 1, it's 1 by k, so it's k by k matrix. Beta hat minus beta 0 is x prime x inverse x prime epsilon, and take a transpose of this beta hat minus beta 0, so we get epsilon prime x prime x inverse so now if we assume that error terms are IID normal, okay, epsilon I, so it's normally distributed with mean 0 and variance sigma square, which does not depend I. Then is equal, then E epsilon prime is equal to sigma square I, which I is an n by n identity matrix. Okay. By the way, now when we compute this variance covariance matrix, we are actually holding condition on x. Okay, holding the data constant. So it's x prime x inverse x prime okay, under this assumption, the error terms is normally distributed with mean 0 and sigma square, which is a homoscedasticity. Then this variance covariance matrix reduced to so sigma square is a scalar that's moved in the front. I is an identity, so it disappeared. So this cancels out with this. So we get it sigma square x prime x inverse. So the variance covariance matrix. However, you should know that this sigma square is actually not unobserved. So we need to estimate from data. The way to estimate is given the beta hat, compute the residuals. So which is epsilon hat, which is epsilon 1 hat for the first observation until nth observation. Then to estimate sigma hat as the sum of epsilon hat squares. divided by n, or divided by 1 over n. Okay, this is the OLS estimators.